We're staring at one of the biggest paradoxes in modern computing. On one side, you've got the most powerful AI systems ever built, and they're consuming the energy of a small city. But on the other side, an architecture that handles incredibly complex thinking using less power than a dim light bulb. This is the great energy divide, and honestly, it's what's holding back the true future of intelligence. And look, this massive gap isn't just about a scary power bill. Not at all. It's about the entire future of efficient, adaptive, and scalable intelligence. This is really the central problem we have to solve if we want to unlock that next huge wave of innovation. Okay, let's just put this into perspective for a second. A big, high-end AI cluster, it can be pulling 20,000 watts from the grid. The human brain, the one in your head right now, it just sips a tiny 20 watts. That is not just a difference, it's an absolute chasm. The brain is literally 1,000,000 times more energy efficient. How is that even possible? So that gets us to the real question, right? Why? What is it about the fundamental design of these systems that creates such a ridiculously huge energy gap? Well, the answer, it's all in the architecture. To figure this out, we've got to meet the contenders. Think of this as a race between three totally distinct architectural philosophies, but they're all chasing the exact same goal: intelligent computation. First up, we've got the reigning champion, conventional AI, running on GPUs. Its strength is its ability to do massive parallel processing, but its design has this critical fundamental weakness. You see, it's built on what's called the von Neumann architecture, which means memory and processing are in two separate places. This forces data to constantly shuttle back and forth, creating a massive data traffic jam, the infamous von Neumann bottleneck, and it just wastes incredible amounts of energy and time. Next, let's talk about the gold standard for efficiency, the human brain. This biological wetware is the complete opposite. Here, memory and processing are tightly woven together. They basically happen in the same place, right inside the synaptic connections. This incredibly elegant design, plus its ability to constantly rewire itself through something called neuroplasticity, lets it learn continuously for a whole lifetime on practically no power at all. And that brings us to our challenger, neuromorphic chips. Now, this is silicon that's literally engineered to copy the brain's blueprint. By using communication methods inspired by the brain and putting computation right where the memory is, these chips go right after that von Neumann bottleneck. The whole goal is to achieve just incredible efficiency. All right, so you've met the players in this race. Now, let's get right to it, the efficiency showdown. How do these three architectures actually stack up against each other when you look at the numbers? Okay, this comparison really lays it all out. Just look at the key battlegrounds here: power consumption, latency, and how they learn. Conventional AI is an absolute powerhouse, no question, but it's super inefficient, and weirdly enough, it forgets things really easily. The brain is insanely efficient, and it never stops learning, but, it's biologically slow. Neuromorphic chips, they're trying to get the best of both worlds, ultra-low power and latency, with that amazing potential for continuous learning. And this might be the single biggest difference of all. When a conventional AI learns a new task, it often just completely overwrites or forgets what it knew before. It's a huge problem called catastrophic forgetting. The brain, on the other hand, uses that neuroplasticity to seamlessly integrate new knowledge with old. It allows for lifelong, continuous learning without ever having to wipe the slate clean. So, what does this mean in the real world? Well, when these neuromorphic designs get it right, the results are just staggering. Get this. IBM's NorthPole chip, which was designed specifically for AI inference, was proven to be 72.7 times more energy efficient than a comparable GPU. That's not just a small improvement, that is a revolutionary leap forward. And it's not just about saving energy, it's also about being fast when it really, really counts. These chips absolutely shatter latency limits, getting response times below 1 millisecond. For real-time applications, like a self-driving car or a robot, where a split-second decision is literally life or death, that kind of speed isn't a luxury. It's completely non-negotiable. So who wins the race? Well, you might be surprised. All the evidence suggests it's not going to be a single winner. The most likely future isn't one architecture completely replacing the others, but a future where each one just specializes in what it does best. And that's really the big takeaway here. The future of intelligence is almost certainly going to be a hybrid one. We're heading towards a world where these very different systems will have to coexist and collaborate to create something much greater than the sum of their parts. So, what does that actually look like? Well, think of it in two steps. In step one, all the heavy lifting of training these gigantic AI models happens up in the cloud, using those power-hungry GPUs that are great at that kind of work. But then, in step two, when it's time to make a real-time decision on a device, like a car slamming on the brakes to avoid an obstacle, an ultra-efficient, super-fast neuromorphic chip takes over. It's the perfect division of labor. Okay, but wait a minute. If these neuromorphic chips are so revolutionary, why aren't they in, everything already? Well, it turns out that despite all their incredible potential, they're facing one last, pretty significant barrier. Let's be clear, the hardware is incredible. It's getting better and better every single day. But the main roadblock, the thing that's really holding back widespread adoption, is the software. The tools that you need to actually program and use these brain-inspired chips are still in their infancy. So what does that actually mean for developers? Well, for starters, there's no easy, high-level coding framework for these chips, nothing like PyTorch or TensorFlow for conventional AI. The programming is super complex and really low-level. There isn't even a universal format for sharing models. All of this creates this massive barrier to entry for engineers who are used to the mature, user-friendly tools we have for today's AI. And this is really where we are today. We have this incredible hardware that can deliver just massive gains in efficiency and speed. But to unlock that potential for everyone, the next great leap might not be a better chip, the better code. So the question we're left with is this: will the future of intelligence be forged in silicon, or will it be forged in software? And whoever cracks that code first will absolutely define the next era of computing.